share the screen. Okay, so here we have it. Let me full screen. Okay, so last time we were discussing electrical field strength, right? So we were talking about electric field strength between different types of charges. We had two different types, like and unlike charges. And we saw that suppose if you have two like charges, they could be positive, positive, or they could be negative, negative. But the condition is that both should be the same. Then you pick any point P in between those two charges. Then at that point P, if I were to bring any other charge, that would experience the electric field as this, which we computed, right? Which would really be the sum of the electric fields coming from both these like charges, right? And that was this thing. Exactly in the same fashion, we computed the same thing if we have two different types of charges that were unlike charges. And in that particular scenario, we would have two different charges, and same thing, we want to find the electric field at any point P between those two charges. What that means is if I were to bring in any other charge from outside and put it anywhere between these two charges, it would feel the electric field, which would be the sum of the electric field of these individual charges. The only difference is because this is a negative charge, there would be a negative sign with that. And when you add those two, they would become this thing. And this would be the total electric field strength that would be experienced by any point P that lies between two different types of charges, right? And that's where we stopped. Any question from this thing?
No, sir.
Okay, all right. Okay, so then let's start discussing electrical potential and hence electrical potential energy, right? So we'll start with the idea of electrical potential. Okay, so remember we have, when we talked about gravity, we discussed gravitational potential, and the gravitational potential for any object was defined. So for example, if this is any mass, capital mass M, and I have a small mass outside this M, then the potential, gravitational potential, was defined as the work that I will have to do in bringing this mass from any distance towards any particular, towards any point in this space that is influenced by this mass. So suppose that I pick a point P over here, that I want to bring this small m, small mass to this point P. The work that I will have to do in doing this is the gravitational potential defined at this point P, right? So that was gravitational potential. Now, electrical potential or electric potential is defined exactly in the same way. The only difference is between the type of field. In gravity, we had gravitational field. In electricity, you'll have an electric field. And now the electrical potential would simply be the work done in bringing any positive charge. Now, we're not talking about mass, but we're talking in terms of charge because we're talking about electricity. So you have to bring any positive charge from any distance. Normally in physics, if we want to talk about a distance that is very far apart, we say from infinity to that point. And if we can call that point P in an electric field, right? So the field is electric in this case. So what would happen is, suppose that this entire region, yellow region, is an electric field, and I have to bring I have a charge over here. I'll draw it like this, and suppose this is charge Q. I have to bring it to some point in this electric field. This is the point P, and this charge has to come to this point P. The work that I'll have to do in bringing this charge to this point P in the electric field is defined as the electrical potential at this point P, right? So this is inside, this is the electric field. So is that clear? Does that make sense? Okay, so that is the electric field, right? Now, to do the ability to do this kind of a work is energy, and hence this is also the electrical potential energy of the system. So now we can write down an expression for this. It's very simple. I'm going to, we all are familiar with this thing that work done is force times the distance, right? So I'll write it as S as displacement. The and we're defining positions with R. So actually, let me use F times R. Now, this force is the electrical force, because the electrical force is going to perform this work. And that force we all know now is K times Q1, Q2 divided by R squared. And then we have this into R. So this is the work done in bringing this charge from any distance infinity to any point P. Remember, the point P should be inside the electric field. Okay, so now this R cancels this square, and you're left with work done, which is essentially the electrical potential energy. I'll call it EPE, which is simply K Q1 Q2 by R. Now, this is the energy. This is the work done, the work that I have to do in bringing a test positive charge from infinity to any point inside the electric field. Now, obviously, you see that there are these two charges, Q1 and Q2. Because there is an electric field already, that means that electric field is produced due to some charge. So at this point P, there would definitely be any charge in this region, in this yellow region, because only a charge can give rise to the electric field. So if I'm bringing another charge, I'll call this Q2 inside this field, then that is when we can talk about the electrical potential energy, right? Now, the electrical potential is just the work that I'm doing for every charge. So I can write that down. Electric potential is essentially the voltage, right? Sometimes it's referred to as voltage potential. We'll represent it with V, and it is the work that I'm doing for every charge. So I'll divide it by the charge. This gives me the potential, or electric potential, as K Q1 Q2 by R divided by Q2. And this Q2 and Q2 cancels, and you're left with K, Q. I'll now relabel Q1 as some source charge, the original charge that is producing the electric field. That is the reason for this yellow electric field. I'm calling it capital Q. So this would be KQ by R. And this is called the electrical potential near a point charge. And that point charge is this Q, which was the reason for this yellow electric field. So we can then write down V as KQ by R. And that is the electrical potential near any point charge. So is that clear? Does it make sense? Okay, perfect. All right. Okay, so that's this. Now, these equations are valid as long as the charge is considered to be situated at the center of any object, right? So the object that we're talking about, if it's a charged object, then the charge should be considered to be at the center of the object. That's what we mean by point charge, right? So point charge. And the point that we are saying that is well, how do I say this? The point that we are considering in really is at a distance that is very large. The distance is very further away from the charged object, right? So this distance, this point P, we said that this would be at distance infinity, right? So the work done in bringing this charge Q2 from some infinity. Because as long as you can say that it is very further apart, you can use this approximation of a point charge, right? And I gave you an example in one of the classes I recall that you can consider an example of stars, right? So you view them from Earth, they appear as very small dots, points. But if I were to be standing in front of a star, it would be something very huge, even greater than the size of the sun. And so the distances should be very large, and then the object can be considered as a point charge. Right. So, okay, so that's this thing. Now we can talk about these potentials in terms of their. So let's pick a charge. Let's pick a charge. Let me go to the next page. And let's see, how does potential, electrical potential, vary with distance for different types of charges, right? Electrical potential with let's call it distance, right, for different types of charges. And so we'll start our discussion with let's say we consider a positive charge, right? So I'm going to consider a positive charge, and this is very simple because we have to remember V is K times the charge. Now, if a positive charge implies plus Q, so this would be KQ by R. And now I can see the relation between V and R, right? And that relation, if I were to consider this charge, suppose this is my charge, and I want to see how would the potential be at the boundaries surface of this charge. So let's try to draw that graph. So this axis, the vertical axis, is my potential, and the horizontal axis is the distance from the charge. Okay, so now when we are saying that we are inside this charge, the potential is maximum, right? So it's some constant value and it's maximum inside the charge. Now, as soon as I reach the surface of the charge, the potential starts to decrease as an inverse 1 over r. And we know that that graph looks like this, right? And this is just coming from this thing that V is inversely proportional to R for a positive charge, right? And so on the left side, it would also be like this, right? So is this graph clear to everyone? All right. Okay. So, okay. Now we can do the exact same thing for this, what do you call this thing? A negative charge, right? So let's take a negative charge. And you can immediately see what would be the difference if you look at the formula. Negative charge means negative Q. So the formula would become V is equal to minus KQ by R. And so now you can see that V is proportional to minus 1 over R if I'm looking at distances and potential. So now for the exact same thing, I'm going to draw a graph, except for the fact that this time the charge is a negative charge. Right? So you can see that this would give you a potential V that is negative or less than 0, right? So the graph will be just the flip of this graph, the one that we had for the positive charge, right? And it would look exactly like this thing. So it's a flip in the vertical direction. So let me try to draw it much better. That will look something like this, right? And then it would keep on increasing to infinity, right? Why is that so? Why does these line keep on increasing to up to infinity? You can see that from the expression. It's very simple, because you can see that V is 1 over R. V is proportional to 1 over R. So as soon as I put 0 in R, the entire thing explodes. It becomes infinity, right? Because anything divided by 0 tends to infinity, right? Any x divided by 0 goes to infinity. So that's why it would keep on, for the positive charge, it would keep on increasing. It would never touch the vertical axis. It would keep on increasing forever. And similarly, in the negative charge, because it's there's a negative sign now, it would keep on decreasing forever. It will not touch this line, this vertical line that we have. It will never touch it, but it will keep on decreasing from there forever. So that's how the potential varies. Okay. So that is this. Okay, now let's try to do an example. Let me consider an example. So let me write it over here. Let's do it over here. Okay, consider that I have a particle, a positive charged particle. And this positively charged particle is moving, right? It's moving in some direction. So I'm going to consider an atom. Say that you have an atom over here, and this is the nucleus of that atom, right? And there is this positive charge. I'll call it positive Q. It's moving in the direction of this nucleus. And I'll give you a speed with which velocity it is moving. It is moving with 5 into 10 raised to power 6 meters per second. Let's try to the first thing is very simple, right? What would be the kinetic energy of such a particle? The kinetic energy of such a particle. It is very simple. The kinetic energy of the particle would be half mv squared, right? So I'll write it as half mv squared. Now, suppose that this mass of this charged particle, let's consider that it's a proton, then it would be 1.66 into 10 raised to power minus 27 kilograms. And then you just put in the values in this thing. The mass would be this thing. The velocity squared, you'd square this expression and you'd put it, and you would get a number. It would be 2.08 into 10 raised to power minus 14. Now it's in energies and everything is in SI units, meters per second, and this is in kilograms. So the units would be joules, right? Joules. Okay, so this was very simple. We just need this thing to do the next part of the problem, which is that you compute, how do I say this? Calculate the closest approach of this charged particle towards the nucleus of the atom. So we want to compute what would be the maximum, or you can say the maximum distance that it can get closed to this nucleus, right? Because eventually it is not going to hit or collide with the nucleus. The reason being that the nucleus is made up of positive charges and neutrons, right? So protons and neutrons. So nucleus, in fact, carries a net positive charge. So positive charge is not going to collide. They are always going to repel each other. So there is a maximum distance that this positive charge can get close to the nucleus, and after that it will bend or change its path, right? So we want to compute this closest distance that the charged particle can cover. So it's very simple. We need to use the conservation laws of energy, and we have to remember how can I compute the electrical potential energy of this particle. So the electrical potential energy of the particle, I'm going to say that all of the energy of the particle that it carries, the charged particle Q, is converted into the electrical potential energy of this particle as it encounters this nucleus, as soon as it gets close to the nucleus. So that means that the total electrical energy of this particle, which I'll represent with some, let's call it E, EP, right? This we know is Q1, Q2 divided by, there's this K, and then you have R squared. Now, what should be this thing? Because of the conservation of energy, this thing should be exactly equal to the kinetic energy of the particle, because the entire kinetic energy of the particle is converted into the electrical potential energy of the particle due to the conservation of energy. So this value will be exactly equal to the kinetic energy of the particle. And then it's very simple, because you just have to compute this value R. Because when it comes closer to the nucleus, it's that time when all of the kinetic energy of the particle with which it was traveling initially gets converted into the potential of the particle. And this can be computed as R. So I'm just rearranging this expression. This would become R is equal to the constant K times Q1, Q2 divided by the kinetic energy of the particle, and then square root this thing, because we have R squared. Now, what would be Q1 and Q2? Q1 would be the positive charge of a proton. So you can you can just take the charge of a proton, that is plus E, right? And plus E, so that charge, the number is, if I remember correctly, it's plus E is 1.66 or 1.60 into 10 raised to power minus 19 coulombs, right? So you just take this. So in place of Q1, I'll put plus E. And in place of Q2 also we'll have plus E. So E times E. So you'll square this thing. And here we have the kinetic energy, and K is just a constant. And then doing the math is relatively simple, right? Okay, so this distance, the distance that I get from this expression would be the distance, or it would be the closest approach that this particle plus Q can come to this nucleus. After that, its path would bend. It would change its direction. So is that clear? What you should be understanding is how I was able to relate the total kinetic energy of the particle with its electrical potential energy. Because when the particle is coming with some velocity towards the nucleus, it has some kinetic energy, right? And we are using that velocity in the expression for kinetic energy. As soon as it comes near this particle, it's not going to collide with it. At some time, it's going to bend and, be deflected back. And because now it has to deflect backwards, it's going to change its velocity, right? So when it's deflecting backwards, when it comes closer to the nucleus, it's going to deflect backwards because they both are positively charged. When it deflects backward, that's when its velocity has to decrease, and then it will start increasing again. So when it decreases, the velocity comes to 0. That's the point where all the kinetic energy of the particle was converted into the electrical potential energy of the particle. So that thing should be clear, right? So any problems, any question up till this part? Okay, so I assume that there is no question, or okay, no questions. All right, so now let's quickly see how can I relate electric field strength, we'll call it E, with the potential difference. So E is the electric field strength. What happens to the kinetic energy? Doesn't it entirely change? Yes, exactly, when it's deflected. So that's what I'm saying, right? So that's exactly what I was saying. So when it is coming towards the nucleus of this atom, it has some kinetic energy due to that constant velocity that it carries. Now that kinetic energy is converted entirely into the electrical potential energy when it's deflected backwards. Because when it's deflected backwards, it's changing its direction completely, and its velocity becomes 0, and then the velocity again starts to increase. So as long as it was having this velocity, which was what we wrote it over here, right? Where is this? 5 into 10 raised to power 6 meters per second. As long as it had that velocity, it has all the kinetic energy. And when it comes closer to the nucleus, it's going to get deflected. As soon as it gets deflected, all that kinetic energy is converted. The kinetic energy goes to 0, and the electrical potential energy goes to the maximum value, right? And that is exactly why I equated the kinetic energy of the particle with the electrical potential energy of the particle, or the electrical potential energy between the nucleus and the charged particle Q. Is that clear? Okay. Now, there will be kinetic energy when it moves in the other direction. But, okay, so let me explain it in this way very quickly on this side, right? So you're familiar with this fact. If you throw something, if you throw a ball upwards, it goes up, and for a very brief moment in time, it stops and then it comes down. So that's how it changes direction. It changes direction by stopping at some point where its velocity becomes zero. In exactly the same way, this charged particle, when it was going to hit the nucleus, it never collided with the nucleus, but at one point, it changed its direction to be deflected and it came backwards, right? So at this particular point, its velocity became zero. And exactly at that particular point was when the kinetic energy was zero, but the electrical potential was maximum, right? And then when it changed the direction and it started moving backwards, then all that electrical potential energy started to convert back into the kinetic energy. So that's what happened. Is it clear now? Yeah, okay, perfect. Okay, so let me just get these on the side. Okay, so now let's quickly relate the electric field strength of a particle to the electrical potential. It's very simple uh, because we saw, if you go back over here, uh, the electric field strength between, you have to recall this thing from AS when you studied electricity in AS. You talked about uniform fields, right? So you had any two plates, for example, and that was a case of a capacitor. So I'm going to draw these two plates. You have these two plates, say one is positive and one is negatively charged. So there will be field lines going like this. There would be some electrical field, these, because of these field lines, they are electrical fields, and they would carry some they would have some electrical field strength. And this electrical field strength is simply the ratio of the potential difference between these two plates to the distance. And that was given by, you can compute this electrical field strength as a force that every charge will experience. So force experienced per charge would be the electrical field strength. And then you can simplify this thing as V over D, where V is the potential difference between the plates, right? It is the potential, so I'll write it as P dot D, potential difference, and D is the distance between these two plates. Now, this expression, you should be familiar with it. I'm not going into its details because this is what you learn in uniform fields in AS. And I'm going to write it in another fashion in terms of a gradient. And that is something that you will learn now, that an electric field strength can be written as a negative